So as Brian mentioned, my name is Ali. I'm part of Google Platforms team, and today with my colleague Tomac, we're going to talk about testing Stratum-enabled switches. We're going to present some ideas that we are hoping that community is going to take those ideas, and we eventually have a Stratum switch stack that is well tested, a production-ready switch stack that they can use easily in production. So what are we going to do? I think you guys all saw Amin's keynote presentation. He showed this pyramid that at the end of the pyramid was availability, and availability is very, very important for the core business for Google networking, right? And you cannot have an available network when you cannot actually validate your switch stack, right? And this is a core part of the network, and if you do not know exactly if it's going to behave well in production, then you simply cannot say my network is available. So we really want to spend some time and think about how we can validate a switch stack well. And since Stratum, in our view, is the future of the switch stack in terms of the enabling P4 and next generation SDN, we need to make sure that we have a very well established validation scenario and validation methodology for Stratum enabled switches. The way that we try to think about validation is black box methodology. Black box methodology, by the way, does not mean that the switch itself is black box. It just means that we treat it as a black box. We do not care about what is running. What we care about is what is exposed from the switch itself. So if we make black box testing methodology first-class citizen, we believe that eventually we'll have a very, very good and well-developed switch stack that can be used in production very well. And why do we actually need this? This is very simple, right? We have too many vendors and too many platforms. We simply, as a company, for example, Google, we don't have enough resources to be able to handle all the vendors in a vendor-specific way, right? This is completely out of the question. I believe all the other operators have the same scenario. At the same time, Stratum comes with very well-defined interfaces, right? And these well-defined interfaces, GNMI, P4 runtime, GNOI, are actually give us some opportunity to think about how we can do the testing more established, meaning that it gives us a very systematic way of do the testing that was not available before, because previously we simply didn't have an interface that was agreed upon by different vendors. So what we're trying to test here is the switch behavior. And when you want to define the switch behavior is the variation of the RPC responses from the switch based on the time variation of RPC requests that coming from the services exposed from the switch and external stimuli. External stimuli is something which is not part of the RPC interfaces. These are things like, for example, port events. Issues with the link. For example, FEC that was mentioned in the previous talk could be actually some sort of an interrupt to the actual platform software that does something internally to the switch, right? So on and so forth. So everything that happens on the switch makes the switch behaves differently in terms of the responses, time variation of the responses, right? We want to test this. At the same time, we believe that the abstraction APIs, P4 runtime, GNMI, and GNOI alone will not be able to define this behavior. You need to do more. These APIs are very generic. They are intentionally kept generic to be able to create multiple, support multiple scenarios. But if you have a generic API, it has this drawback of having so many different ways of interpreting the same thing. Also, because the API is very generic, the number of corner cases that you can imagine is going to be exponentially large. So it would be very, very hard to test all the corner cases. So what we propose is that instead of trying to define the behavior of the switch in terms of like English language or some documentation, try to define this behavior or the expected behavior in terms of tests. This is going to work the best because we will have a very systematic way of defining what a specific switch, which is, for example, running on a Stratum switch stack, is going to behave. So the APIs which are P4 runtime, GNMI, and GNOI, plus a set of compliance tests are going to be your contract. And you have this contract, you will give this contract to everybody, and all the vendors or the switch providers will be able to run this test to make sure that they comply with this contract. And at the same time, in order to make everybody's life easier, we want to automate this test generation, meaning that we need to devise ways that we can easily increase the number of tests or test coverage that we have. So the way that Tomac and I thought about how testing could be done is somehow explained in this feature. We're thinking about a case that humans will have two ways of defining the test scenarios. One way is to somehow separate the actual test definition from the test infrastructure. I will talk about this thing called test vectors and to see how exactly this will be done. And the other way is to actually define some sort of a very simple scripting language that defines very complex scenarios. These scenarios are scenarios that you cannot simply script using the actual APIs that you have. These scenarios will be then translated using some sort of a transpiler or compiler to a set of test cases or test vectors if needed. And these test cases or test vectors will be fed into a test framework, and test framework will easily replay that test for you. In addition to all of those that are manually generated, we will have some cases that based on some input, some automatic test generator will be able to generate test vectors for you. So I'm going to talk about test vectors here in the next set of slides, and then Tomac is going to take over and talk about CDLang, which is an scripted language for defining complex scenarios, and he's going to talk about it in the context of the GNMI testing more. So what are test vectors? So the idea behind test vector was very simple. We were assuming that everybody, especially like big vendors, like Google, AT&T, Comcast, and everybody, they have their own way of testing stuff, right? And it would be very hard for them to change the way that they test switches to comply with the new test infrastructure, right? So what could we do? Something that we could do is to actually separate the definition of the test from the actual test infrastructure. So if we can have a way to define the test without even caring about the test infrastructure, this very same test infrastructure can be run by multiple vendors, whichever way they want, to actually comply with some sort of a compliance test that we have. The assumption is that we have a black box. The black box is a box that we do not know or we do not care for the sake of testing what is running on it. But what we know is that it's compliant with a set of P4 runtime, GNMI, and GNOI APIs. And we have a way to systematically trigger some events on the switch. This is very, very important for the sake of testing. As I mentioned, since the way that we actually trigger events are not part of the APIs, we have to have a way to be able to handle that. For example, we will have port events. We will have fan issues. Inserting all sort of failures to the switch stack is going to be done using this. If we have this, mathematically we can define test vectors as a set of what we call test cases. Each test case, let's say you have 100 test cases in a test vector, is going to be a tuple of the set of operations, the set of external stimuli, and the set of expected behaviors or expected responses from the switch, right? So if you somehow combine the operation and external stimuli as whatever changes or defines the behavior of the switch, you can assume that this is what I change as part of a test, and this is what I expect to receive from the switch at any point of time, right? The idea or the promise here is that using this set of test cases and starting from initial state S, you can deterministically move the switch to a state S0. You can deterministically move the state to S1. And there is no other external information required for this. Another thing that we need to be very clear about is that these test vectors are vendor agnostic, but they are not topology agnostic, meaning that it matters what hardware I'm talking about in terms of the port count, in terms of which port exactly I'm talking about, the speed of the ports, and so on and so forth. The topology awareness and vendor agnostic are two different things. So we can, any pizza box with 32 port, which can run in 100G, 10G, 50G, and 20G, for example, are good. But we cannot assume that I don't care about the port count, or don't care about the speed of the tests. And these test vectors are generated based on some input data, right? So these input data could be some human input, right? And could be the P4 specs that are given for a specific switch. It could be the topology data. Again, the topology data is what I mentioned in the previous slide, what kind of chassis I'm talking about, and maybe like a trace of operation. In SDN world, we know that if you have a use case in production, there is a SDN controller that has been running for a long, long time, right? So trace of the controller and interaction of the controller with the switch would be the best source of data for you to be able to understand how the switch should behave. So all these input is going to be fed into a test vector generator, which is an automated way that defines, generates the test vectors, or it could be generated by humans. For test vector generators, there are so many different things that you can do, but the most promising way so far is called the ATPG, Automatic Test Package Generation, based on P4. There are a few universities and companies that are actually working on that, and we were thinking that this could be actually adapted here. And in terms of what is the format of test vectors, at the moment we are using protobufs, because protobufs are the ones that are used by the RPCs as well. So encoding test vectors using protobufs is actually making the most sense, right? So this high-level view will tell you how exactly in future a Stratum-based switch is going to be tested. So we'll have the P4 spec, topology information, and the STM traces going into a test vector, right? At the same time, there will be some test vectors that, for example, a vendor will give us, right? In future, maybe we'll say that a vendor X, for example, it knows that there is a specific behavior of the switch that needs to be tested over and over. We will have that as part of our test vectors as well. And we will have some handcrafted test vectors. Somebody will just go and sit down and have, some test vectors generated for any specific purpose. All of them together is going to be a collection of test vectors that will be in a source control database, either GitHub or, Perforce or whatever we will use in future. At the moment, is going to be part of. We're hoping that it's going to be part of the Stratum code base itself in GitHub. And then we will have this test vectors will be fed to a very, very simple test framework. We call it, test vector replay code. That all it does, it gets these test vectors. That could be a lot of test vectors, by the way, and replay them on a specific single switch. And that blue box over there is a box that will be used to do to generate this external stimuli. Could be an Ixia. Could be a commodity server, anything that will be used to be able to, for example, generate traffic and push it to the switch and create external stimuli can be used here. And what we use to actually test or interface with that blue box over there, that one is still work in progress. We don't have a common way to do that, because we will have multiple ways of doing so. Maybe at the end of the day, what we end up doing is that this test vector will have different drivers for different test generators or traffic generators, that depending on what you have, you will just pick one of those. And definitely community can help with that part as well. So this is the high-level view of doing the test vector testing for Stratum. So I'm going to hand over to Tomac, and Tomac will tell you that in addition to the test vector generators, we will have another way of defining more complex scenarios. At the end of the day, what's going to happen is that we will have a couple of systems or a couple of frameworks for doing the testing, and the users or the community members have the option, have the freedom of using either or both, depending on their use cases. Because at the end of the day, no test framework is the best test framework, right? If you have an option of getting the best of whatever works for best for you, then this is the way to go. So this is another, at the end of the day, this is another way that tells you how exactly after we have the test vectors, the qualification will be done from the point of view of a vendor operator. So after the test vectors are going to be tested or used by the vendors. We're going to go and run some functional tests that actually reuses the test vectors. The output of these functional tests can actually itself be used to create more test vectors. We, for example, understand that, oh, one scenario was left. I forgot about this scenario. I'm going to go ahead and quickly add a test vector for it. And then after all of this were done, we will put the switch in a more rigorous integration testing in a very large fabric. And all of those, if there are some issues with it, we will go back to the vendors and say, here is the test vector that was failing. So very clearly, the vendors will know what is failing. As opposed to writing it in English, we'll have a very clear way of telling vendors what is wrong. And finally, if all of those are passing, we say that the switch stack is actually qualified, and then we'll go for SDN qualification, or in some cases, if there is no SDN, just goes to production. Anyways, that's what I had. So I'll hand over to Tomac to talk about C-Lang.
So I assume that by now you think that all of this is great ideas, how it should be applied in the reality, right? So let's take something smaller, just one of these interfaces, and see how we apply those ideas to testing GNMI. So first, maybe a small correction. When we say GNMI, we usually think about the whole configuration and monitoring system, while the GNMI is just the protocol which defines a set of RPC calls like get, set, subscribe, and the wire protocol using gRPC to communicate with the switch. What's needed to more are the OpenConfig models, which are defined using the Yang language, and a way to translate those models into the GNMI, into the data which can be transmitted using GNMI or gRPC, so into protobufs. So, when you look at it, you think, okay, that's a lot of information, right? We have the data in the form of a tree, where each of the leaves represents some interesting piece of information. We have information how to get it. There's those Yang paths. We know how to transmit it on the wire. We get the RPCs to get them. We have the information how to subscribe for changes, things like that. That should be enough to have the smooth interoperability between vendors. Unfortunately, this is not true. The problem is, as Ali said at the beginning, is that those documents describe a static model. There's no information about how this model should behave when there's something changing, right? Say an interface goes up, which of those leaves should change their values? Say operator changes the administrative state of the interface. Which of the leaves should change? If somebody has subscribed to those leaves, what kind of information should be sent to this client application? What messages, in which order, and what would be the fields saved there? All of this is missing. So how we solve this problem? We are solving it by defining these scenarios, right? This is a scenario is a precise definition of the messages being exchanged, their contents, their order, for all the interesting cases. Of course, there's a lot of possibilities how to encode or how to document those scenarios, right? One of the options might be using Google's unit test framework and just write a program which will be executing those scenarios, sending some messages, expecting some responses, checking if the fields contain whatever they're supposed to contain, but it's kind of not very portable. There might be some great frameworks used by other companies who say using Python, I don't know, and suddenly all this great list of scenarios cannot be used. They have to be first translated into this other framework, right? And this will have to be done manually by some person who might make a mistake or misinterpret something. So we have decided to go with a different approach, define a domain-specific language just for the purpose of testing GNMI. By doing that, we get a number of things. First of all, we limit the scope of the whole problem. And so whatever will come up in the form of a syntax of this language gives us, is focused on testing GNMI. We get a language or scenarios which can be processed by a machine, right? So this allows us to go to achieve a number of things. We'll be talking about this a little bit later. And of course, we get something which is human readable, especially if we'll make sure that those scenarios in this language is focusing only on the important things, the sequence of the events, the messages which should be exchanged, the fields which should be set, and nothing else, leaving the rest for the actual implementation of the test framework by somebody who is interested in doing this. So let's jump and see a Hello World program written using this language. So it's this really the most simple example. There are two messages. There are the first one on the very top. Get request is the message which is used by GNMI to request a value of a leaf from the server, from the switch. You can see the path of the leaf we want to get. There is some extra encoding information which is required by GNMI to return the right response. And then you have information what we expect to get in response for calling this gRPC call. So we expect to receive an OK message, success, and the message with the response where we see, again, the same path and some value. As I said, we tried to design it to make the things simpler for the human and not impossible for the machine to understand. And there are a few interesting pieces here shown. First of all, this underscore at the very bottom, it means the any value, which means, in some scenarios, you simply are interested in receiving a message. The value in it's not really that important. The importance is that it's there, because it means that the information has been added. We didn't want to limit ourselves to hard-coded values. Say you might want to execute this scenario on multiple interfaces. So instead of using just writing it for separate scenario for each interface, we can use a parameter which is parsed as a parameter to this scenario. So in this particular case, we have the interface name. And one more thing, the whole thing, this language has a built-in support for versioning. We know that, in time, all the protocols, models, they all will evolve, and there will be changes, right? So instead of using some concept from, say, C, like #if, def, something like that, we have built in the support for versioning. So you specify in the first line of the scenario the version of this scenario, so you can have multiple versions of it in the suite. And when you will be testing a device, you specify the version of the specification you would like to execute, and then this scenario will be executed. All right, one more example, the last one, a little bit more complex because it's using the streaming interface, the streaming functionality provided by the GNMI. So the first line is creating the stream, right? The stream is created by calling the subscribe RPC. Once you have the stream, you send a subscribe message. This one is kind of strange, subscribe, because it's just, you just want to receive once all the information. But again, you specify the path for the value. You please note the star by the name. It means that we want to see the if indexes for all the interfaces. And then once the message is sent, we expect that there will be a bunch of messages coming back from the server, from the switch. So, and those messages are handled in this green and yellow boxes. The first one is treated in a special way. The purpose of this whole code is to learn the name of the very first interface. So in the line where we received the message, we assign the name of the interface to a local variable. And all the following messages will be ignored. We still expect them to be received, but by using this any value for the path and for the value of this leaf, we kind of just make sure that they are there, but we ignore the values. And the last message to be received is the message which is defined by the protocol, the GNMI protocol. It has to follow, all the messages. It's like kind of a dot in a sentence saying, okay, that's done. No more. There will be no more messages. And then we close the channel. And the last line here, the execute example one, is the way you can use this value of the interface name you learned to execute the very first program, the scenario I showed you on the previous slide. All right, so what are the usage scenarios we came up with when working on this tool? Of course, the major idea was to create a language which will allow us to define scenarios and automatically generate test cases for us. But the whole thing is not limited to that. If you think about it, once those scenarios are written, you can run some analysis on it and find out what paths or what scenarios are really being used, right? So this can constitute a contract between the client and the server, because you specify exactly the scenarios which can be used on this interface, right? So by having that, the development team on both sides really can focus on implementing things which are important because they are supported. I mean, they are expected to be supported, and they can ignore things which are not really that important. There's the GNMI specification allows you to specify the paths to those leaves in so many ways that it's really hard to keep track of them. So if you can see that, in this particular deployment, the leaves will be accessed only in some one particular way, why to waste resources to implement all the others, right? And also the computing resources on the switch when the request will be coming in to parse those paths. Okay. So, what we have done so far? I mean, all I have shown you is already implemented, and we are using it. We have implemented the tool, the transpiler, which is taking two inputs, one of those scenarios and a template written in Golang text templating language, and the scenarios are analyzed. The information is learned from it, and then it's passed to those templates, and those templates are used to generate Google unit test code, which is then compiled, and when executed, it's executing those scenarios, all the checks, all the things on the real hardware. We have it integrated in our development process, and we execute them every night to make sure that we haven't made a mistake during the day. What's to be done? We need, of course, more scenarios, because what we have covered so far is just a small percentage, and we hope that if this whole thing will be accepted by the community, there will be more scenarios coming the way, and that will help us to test the scenarios. For that, there's this. I assume that once we have more scenarios, more likely we'll find out some problems with the language, so some fine-tuning or maybe extensions will be needed. I think it's acceptable and expected. We need to write some tutorials and manuals, and actually, the third point is kind of done already. It's part the code is part of the Stratum code base. Okay, thank you.
I think we have time for maybe one or two quick questions for them.
Thanks for the presentation. So I see how CD-lang can be used to write kind of test vectors for GNMI, but how do you handle test vectors for the rest of the test framework, the control plane and packets themselves?
Actually, we think P4 runtime is the easiest for test vector. And when we started with test vector, we actually started with P4 runtime. And we have a lot of test cases right now that support P4 runtime. GNOI, again, is very, very simple. It's very operation oriented. What was the hardest was GNMI. And one of the reasons that Tomacs helped us create this beautiful language is because we felt like it's missing. It's missing some way of defining complex scenarios that GNMIs need to handle. So we can tell you that test vector can handle all these three cases. GNMI is the one that, in addition to test vector, we feel like will benefit from the CD-langs the most because the scenarios will be more complex.
I think there is, one more question.
Yeah, you guys were talking about scenarios and external stimuli. Is the description of something like a port down event from an external cause, like shut off port, is there a definition for that?
Yes, exactly. So the test vector is going to have a set of possible. It's sort of we're using the one-off in the protobuf. It's like a specific semantic. It says one of these cases. We have like multiple test cases using port events, chassis events, line card events, and the port events could be the port up and downs. Could be, QSFV removal, for example, all sort of crazy stuff that you can easily emulate on the switch will be there. And of course, it's not complete. We're assuming that more and more is going to be added to that. What is missing right now is that blue box that I've showed, which is the tool or the external device that will be connected to the switch to be able to handle all of those emulations. For test traffic generation, hopefully we have a lot of cases, like we have Ixia, we're seeing over there. We have commodity server, but for things like port events and some of the crazy things like emulating the QSFE removals, it becomes a little bit vendor specific. That's unfortunate, but that's how it is, because the platforms are different from one vendor to another. Yeah.
Thanks again.